Today, I would like you to connect what we've been talking about when it comes to food relationships and webs and energy flow to the matter that's being also cycled during these feeding relationships. In nutrient cycling, I'd like you to not only understand how carbon, water, nitrogen, and phosphorus move through our system, but also really what is our impact and how do we alter these cycles. That's really going to be our focus. These are also called biogeochemical cycles in addition to nutrient cycling, and this really highlights that these chemicals are moving through living and non-living components of the ecosystem. And I think it's important that we pause here and remember that all consumers that are not autotrophs really depend on that first link to transfer these biogeochemical cycles to consumers, and that first link is plants. So the connector that brings the hydrosphere, the atmosphere, and the lithosphere together in the biosphere is plants. When plants take these nutrients up through their roots, then they can transfer them to consumers. So of the biogeochemical cycles or nutrient cycles, we're going to focus on carbon, nitrogen, and a little bit on phosphorus. Water is so important, and we've changed the water cycle so drastically. We're going to focus on this in its own separate unit later this semester. After reading in your textbook, pages 85 through 90, you really should be able to come back to the different diagrams here and fill in some of these components, both what occurs naturally and ways that humans have impacted the system. So I'd like you to return to this after doing your reading. The carbon cycle is super important because we are carbon life forms. And without carbon, we can't build life as we know it on this planet. Probably the molecule you're most familiar with is carbon dioxide, because that's the gas that plants take in and convert to carbon compounds like glucose through photosynthesis. Carbon dioxide is not super abundant in the atmosphere, but is essential for getting carbon into plants and then transferring that carbon to consumers. There's kind of four places you're going to find most of the carbon. You have CO2 in the atmosphere, and CO2 can be dissolved in oceans. And then in land, you're going to find a lot of it in soil and in rocks. And we can't forget the organisms. So all the biomass of organisms in the ecosystem also store large amounts of carbon. And then plants in the past that have decomposed can store that carbon in fossil fuels. And so what we're really talking about when we're talking about emissions of carbon is we're really talking about finding an old store of carbon compounds from living organisms that has been, transformed over time, and we're unleashing the carbon in the fossil fuels that has been stored. And this is also why fossil fuels is not a renewable resource, right? Because these were created so long ago. Just pause here to please remember that plants take in CO2 during photosynthesis, but both plants and animals release O2 or CO2 during respiration. Okay. I really want you to think about sinks, because when it comes to how humans are impacting the carbon cycle or the nitrogen cycle for that matter, a lot of it has to do with how we are changing the sinks or the storages of where carbon is kept. So if you go to a storage and you release the carbon from that, you may upset the balance of available carbon in the biosphere. So carbon sinks are where large amounts of carbon are stored. They're stored in soils and in the organic material that is decomposing, and in the rock. Soil is made of both living and non-living parts. There's a ton of carbon stored in the biomass of forests, but by far our largest sink of carbon is that of the oceans. If you were to look at how much carbon the ocean, carbon dioxide specifically, is dissolved in the ocean, it is currently the largest carbon sink on the planet, storing more carbon than all of our forests combined on the entire globe. So when we talk later on in the year about how temperature of the oceans impacts its ability to store carbon, this is a really serious, impactful change that we might have on our planet by, warming the oceans and decreasing their ability to store carbon dioxide. Okay, other ways we impact the carbon cycle is obviously we burn a lot of fossil fuels. We burn it to transport our food on trucks. We burn it to warm our houses. We burn it to drive to our activities. And we know that this is contributing to climate change and increased global average temperature. We also produce a lot of methane in the livestock that we raise for consumption, and we release a lot of methane from landfills. Now, CO2 and methane are similar, but methane has a larger warming potential, which we'll talk about later. Too much carbon dioxide or increased levels of carbon dioxide over a very short period of time has led to a lot of coral bleaching on very, very large scales. So if we're reviewing the carbon cycle again, can we think of ways that it naturally is stored in the biosphere? Can we think of ways that humans are impacting those storages? And can we think of other activities where maybe we're taking a natural cycle, but we're amplifying the scale in which it occurs? Okay, so what are the ways that humans impact the carbon cycle? Let's switch gears to the nitrogen cycle. I love this cycle. I think it is fascinating, and it's really, really easy to see the links between the nitrogen cycle and our food supply. Nitrogen is super important because it helps your body make up DNA and molecules, and it's one of the limiting factors of plants. So if you have nitrogen, if you had limited amounts of nitrogen, you may limit the production of plant material, which we know is the base of all food chains and the first step in how productive an ecosystem is. So if you look at the atmosphere, it's almost all nitrogen. 78% is nitrogen. Take a big breath of air, it's going to be nitrogen, right? The remaining percentage is oxygen and then some trace gases. So I think that, it's fascinating that of the most abundant gas on the planet, okay, in the atmosphere, we can't use the nitrogen gas we breathe. And in fact, we really depend on other organisms to do it for us. A quick stop here. I really want you, I'm going to show you more detail than you need to know in terms of like any form of assessment or demonstrating human changes. But I do think it's important that you can go back and access the different forms, but you do not need to know specific, processes, chemical formulas for denitrification and nitrification or chemical compounds. I will review some of that with you so you have that background information, but I won't assess you on it. But you do need to know that bacteria, living parts of the biosphere, are absolutely vital. They live in the soil and they convert unusable nitrogen gas into a form that can be used by plants and then transferred to humans. If plants can't capture the nitrogen, their tissues will not contain it to transfer it on to consumers. Okay, there's this great video here that I've linked in Google Classroom. I highly recommend that you watch. So here's some of the stuff you don't necessarily have to know. Atmospheric nitrogen, or N2 gas, is very stable and non-reactive. Okay, and because of that, no matter how hard, or how useful it could be, plants can't use this unusable form of gas, and definitely humans can't either. Okay, but bacteria living in the soil can take that nitrogen and convert it into ammonia, which is usable by plants. And this is what you need to know right here, that bacteria are a critical link from taking nitrogen gas in the soil and converting it into a form usable by plants. That helps the plants build nitrogen into their tissues and then transfer it to others. And lightning can break the bonds to and convert gas into different forms. Again, you don't need to know necessarily the different chemical compounds, but do know usable and non-usable nitrogen. There's a critical link with bacteria in the soil. Some of the impacts of nitrogen cycle is that we need to add nitrogen to continue our intensive farming so that we can have this industrial scale farming And using intensive agriculture like this depletes the nutrients of the soil. So we have to add it back with fertilizers, okay? And a lot of times the application of the fertilizer itself, the excess nutrients can run into our water supply. And because nitrogen is a limiting factor of a lot of plants, it will create increased productivity of algae until they create what's called the algae bloom. And when it dies, it can create the dead zones, which are making the news. Oops. Fertilizer requires also a ton of energy input to make it. It's not like you just go to a hillside and you collect a bunch of fertilizer. You have to basically convert this, non-usable nitrogen into a usable form, and that requires a lot of energy. Remember, in nature, lightning can do that, right? So it's a lot of energy and it has its own climate impacts itself. And then there's all these additional inputs by needing to convert nitrogen into a form we can use as fertilizers, like the pollution from the cars and the nitric oxide that can be produced. Something to note right now that, we depend so greatly on converting nitrogen into fertilizer to create, industrial scale agriculture. We have doubled the amount of nitrogen that transfers through the biosphere. Doubled it. It's kind of an unfathomable scale that we've created. Okay, phosphorus cycle has a lot of similarities to nitrogen cycle and how it's used in ecosystems, but the big difference is that the phosphorus cycle doesn't enter the atmosphere, and instead is a very, on a geologic timescale, adding new phosphorus to an ecosystem is very slow. It comes from the erosion and weathering of rock. So one of the ways that humans impact the phosphorus cycle is that if we add it at a quicker scale than would naturally occur, we can create things like algae blooms or disrupt the balance of producers and consumers. We use phosphorus for our DNA, for our nucleic acids. It's very important for the tissues in consumers. As a limiting factor for plants, if you add more of it to an ecosystem, to a certain point, you receive more plants and more productivity. The storage of phosphorus really is in rock itself and in soil. And this is a review of what we talked about, but one thing we haven't discussed a whole lot is the absolutely critical role of decomposers in returning phosphorus to the soil from plants and consumers. Without the decomposers, it would look more like a straight line, the cycle if you drew it out, right? But decomposers break down the tissues in plants and animals that hold the phosphorus and they return it to the soil so it can be taken up in the biosphere again. Our impact on phosphorus is similar to nitrogen in that phosphorus is in a lot of our fertilizers, and that excessive runoff can create increased productivity and then dead zones following. Phosphorus, though, is in a lot of our human waste, okay, and in animal waste in general. And so untreated wastewater from humans, so our urine and our feces, if it's untreated, it can carry nitrogen and phosphorus to water systems, but also our incredible industrial scale, livestock raising animals to consume as meat has produced a ton of phosphorus, which can contaminate water supplies. And we'll talk more about this later on too, in that, a lot of communities that are impacted by the waste that runs off of these are, communities that have less power. And so there's a major environmental justice issue tied to some of where this waste goes. There are some very good review videos here, in addition to your textbook, which I think does a good job really giving you just the nuts and bolts of nutrient cycling. And I think a good test could be to pause here and see, could you draw in some naturally occurring parts of this cycle and then some human impacts to these cycles. Again, we're not going to hit water until later, but we're going to focus heavily on carbon and nitrogen and kind of link in what's similar to the phosphorus cycle. Thank you.